So let's study impedance matching. Impedance matching. Yes, let's study impedance matching. So what is impedance matching? Source. Suppose you have source transmission line load. The transmission line wants to see ZL equals to Z0, but here 100 ohms equals to is not equal to 50 ohms because we have load impedance 100 ohms and plastic impedance 50 ohms that causes a reflection, and therefore some power travels toward the source. Matching means we arrange things so that the impedance seen by the line is Z seen equals to Z0, then reflection coefficient equals 0, and VSW equals to 1, so maximum power is delivered to the load. How can a transmission line itself help matching basis where the input impedance equation becomes useful? Zn equals to Z0 as ZL plus JZ0 is the tan beta L by Z0 plus J beta L tan beta L. Notice tan beta L this time tells us how the impedance matching we see changes depending on the length of the transmission line. So instead of changing the load, you can choose an appropriate length of the transmission line to transform the impedance. It's called impedance transformation. But where does the NBTL come from? It comes from the wheel traveling along the line. For a lossless transmission line, beta equals to 2 pi by lambda, where lambda equals to mu and beta equals to phase constant. As the wave travels a distance L, its phase changes by beta L. So, for a lossless transmission line, we say beta equals to 2 by lambda, where lambda equals to wavelength and beta equals to phase constant. Uh, Lambda equals to wavelength. So, the wave travels a distance L, its phase changes beta L. So, wavelength is L. So, beta L is simply the electrical length of the transmission line. The sine or cosine behavior of the forward and reflected wave eventually produces tan beta L. You don't need to think tan as some additional physical component. Why is the length important? For example, L equals to lambda by 4. Then beta L equals to 2 pi by lambda by 4, pi by 2. Therefore, tan beta equals to tan pi by 2, which becomes extremely large. Tan 90 is 1, right? Tan 45 is 1, right? This produces a impedance transformation for a quarter wave line. Zn equals to Z0 square by ZL. This is why quarter wave transformer is useful in impedance matching. Quarter wave transformer Z0 square by ZL. A simple example, so Z0 is 50, ZL is 100. If you use quarterly transformer characteristic impedance, Z1, we want input impedance to become 50. So Zn equals to Z1 square by ZL. 50 equals to, this is characteristic impedance, Z1 square by 100. Then Z1 square equals to 5000. Z1 equals 70.7. So 70.7 quarter wave section transformer the 100 ohms load into quarter wave section transforms the 100 ohms load into 50 ohms. Conceptually, 50 ohms line, 70.7 wave section and 100 ohms load. See approximately 50 ohms. The line is now met. What you should remember for you is impedance matching is Z equals Z0. No reflection AWR. Phase constant 2 by lambda. So Zn equals to Z0 square by ZL. Here we see again why it is important. Which becomes extremely large. This produces special impedance for a quarter wave line. Quarter wave line is uh, this is why quarter wave transformer is useful for impedance matching. Zn equals to Z0 square by ZL. A simple example, suppose static impedance equals Z0 50, ZL equals to 100. If we use the quarter transformer with characteristic impedance Z1, we want it to its input impedance. Actually, I am unable to understand this section. So yes, the problem is that we jump to quickly from the general input impedance formula to quarter transform. Let's forget the complicated formula for a moment and understand the idea physically. Start the problem. Suppose we have 50 ohms transmission line, 100 loads with the load. The line has Z not equal to 50 ohms, but the load is ZL equal to 100 ohms. They don't match. Therefore, there is a reflection. We want the 50 ohms line to see 50 ohms at the input. We insert another piece of transmission line. So, we want this 50 line to see 50 ohms at the input. So, we insert a piece of transmission line, 50 line, 100 ohms. We insert a special line. This special line is called quarter wave transformer. Its length is L equal to lambda by 4, but it also has its own characteristic impedance. Let's call it Z1. So 50 ohms Z1 to 100 ohms. What does this special piece do? Here's the important idea. The quarter wave section changes the impedance that you see when looking to it. It transforms ZL into another impedance at its input. For a quarter wave section, Zn equals to Z1 square by ZL. Notice carefully Z1, not the original 50 ohm line, appears in this formula. Now use our numbers ZL equals to 100, Zn equals to 50, 50 by Z1 square, then Z1 square, Z1 equals 70.7 ohms. So this is line actually. This is line resistance, line impedance. Uh, Here Zn means line impedance. We got Z, we got Z1, we got Z1 as 17.7 ohms. Now when the 50 ohms line looks into the 70.7 quarter section, it means 50 ohms. Therefore, Zn equals to 50 and Zn equals to Z0. So the original line is matched. But why does the quarter wave section transform impedance? This is the part that you usually can remember our general formula Zn equals Z1, ZL plus JZ1 tan beta L by Z1 plus JZL tan beta L. For a quarter wave line, L equals lambda by 4, beta equals 2 pi by lambda, beta L equals to 5 by 2, so tan beta L equals tan beta, which tends towards infinity. But when that happens, the dominant term and the numerator denominator once containing tan beta L, the common terms cancel. Zn equals to Z1, then Z1 square by ZL will form. So this is the easiest mental model. Impedance transformation 100 ohms to 50 ohms. The 70.7 ohm section doesn't simply behave like a resistor, it is transformation line section, and because its length is extremely lambda by 4, exactly lambda second, the electromagnetic wave traveling through it transforms the impedance. So don't think 70.7 ohms resistor is connected. 70.7 characteristic impedance transmission line with lambda length. That's a completely different thing. One more very example. Suppose Z0 equals to 50 and the load is ZL equals 25. We want transform 25 into 50. So again Zn equals to Z1 square by ZL. 50 equals to Z1 square by 25. Z1 square equals to 35. Z1 equals 35. So 50 ohms line, 35.36, 25 load. Mm, we can also stick that 35 plus 25 gives 50, right? 54 like that. Here also, if we take 70.7 plus 7 plus 5, we can tell it gives some impedance. So, when talking about Zn equals to Z1 square more Zl. Here Zn is not force impedance. Its original transmission of impedance to make the impedance match. We have to quarter transformer is the quarter transformer changes the Z0 wherein we want for the match. Yes, you got the main idea just on technology correction. Suppose original transmission line is 50 ohms, ZL equals 100, there is a mismatch. We insert a quarter wave transformer, lambda by 4, Z1 equals to 70 by 0.7 ohms, ZL equals to 100 ohms. Uh, the quarter wave section transforms the 100 load into a input impedance seen at the beginning of transfer. Zn equals Z1 square by ZL, which Z1 equals 70.7 ohms, ZL equals to 100 ohms. Zn equals to 70.7 by 100 gives 50 ohms. So the original 50 transmission line now sees Zn equals to 50 ohms equals Z0. Therefore, it is matched. Here Zn is not perpendicular, correct it is. Zn is not the source internal impedance, means the impedance seen when looking into the quarter transfer from its input side. So the transformer directly makes the 100 load look like 50 ohms to the original transformer in the mental picture. 50 ohms transmission line transforms the load, so yes, quarter wave transform changes impedance seen the original. And then the original signal, original line is matching no reflection. SWR equals to 1. So here Zn means the original line. The formula also Zn means in the formula also Zn uh, transmission line plus circuits. We are talking about fourth internal impedance. Yes, Zn can mean different things depending on circuits I context. The simulator does not automate source internal impedance. In the ordinary circuit, Zn will often mean the input impedance of the circuit provides. What the source feels when it looks into the circuit, for example, yes, source here ZS and the circuit looking in Zn, circuit looking in here Zn is the impedance presented by the circuit, not ZS. The source's own internal impedance would normally be ZS. It is in a transmission line source looking in Zn. Zn equals to impedance seen looking into the transmission line. Zn is not equal to Zs. Zs is the source internal impedance. It is looking to the transmission line, that's the internal impedance. For the quarter wave transformer, so then Z0 is the characteristic impedance of transmission, but that is difference between what is difference between Zin and Z0 on transmission line? Both are both use transmission line in your definition. Hmm. Exactly, this is the important distinction. Both Z0 and Zin are associated with the transmission line, but they describe two different things. Z0 property of the transmission line, characteristic impedance. The transmission line itself has an impedance, it is the resistance, but impedance, so AC signal, we say impedance, is determined by the physical electrical properties of the line. Plus G omega G plus J omega C for loss plus and Z naught equals to root over omega C. So Z naught equals to the property of the cable itself. Changing the load doesn't change the cable Z naught. Yet in what you see when looking into the line now, take the same epsilon cable. Z in asks if I stand at the input of this cable, what impedance do I see? That does